how much is known about climate change in the past, and why is it such an issue now?
Okay, so we have quite a lot of data that's been taken from ice cores, for example. So if you drill down into the snow in Antarctica, it's about 3 kilometers thick. If you get right to the bottom, the ice at the very bottom of the Antarctic ice sheet fell as snow about 1 million years ago. And
so they go back 1 million years, the ice cores?
Approximately, yes.
Okay.
So if they look at the isotope ratios of the oxygen, for example, in the water that's in the ice, they can infer what the temperature was at the time that the snow fell that formed that ice. So you've got a temperature record going back that far. And also there are air bubbles that were trapped in the ice as the snow fell and formed. And so by crushing that ice and analysing it using various instruments like mass spectrometers, you can measure the concentrations of certain gases that were present in the atmosphere up to 1 million years ago. So that's where a lot of the information has come from, from a long time ago. But of course, more recently, we've got direct measurements in the atmosphere, from various instruments. Carbon dioxide has been measured since 1958 from the top of a extinct volcano, for example, using infrared spectroscopy. So there are methods that can be used to make actual measurements, and we can infer what it was going back in time, for example, using ice cores.
So how reliable are ice cores?
There's obviously some uncertainty in what the actual age of the ice is, and that uncertainty becomes larger as you go deeper and deeper. There's been lots of checks and balances. You can link certain things that happened, for example, in 1830 or something, with some big volcanic eruption that took place that year. So there's some marker in the ice that you see that came from that volcano. So there are certain things that you can tie in the age to sort of do a calibration. So there's various things that have been done. But there's no doubt there is some uncertainty, but it's not a large amount compared to the actual age itself.
So why is this modern global warming we're facing now any different to, for instance, the warm period we had in the Middle Ages? I mean, there's stories of vineyards all across England during the Middle Ages. That was obviously due to global warming. Why is it a problem now and it wasn't a problem then?
Yes, and that relates to the first part of your first question. Sorry, the second part that I didn't answer. So you're absolutely right. The temperatures at the moment are... they've been this warm in the past. In fact, they've been warmer than they have been now in the last 1 million years. And of course, there have been some very cold periods as well, like the ice ages, and the Thames used to freeze over and so on. People used to skate on the Thames. What's different now, though, is that the concentration of carbon dioxide, methane, nitrous oxide, or laughing gas are much, much higher now than they were at the times when the atmosphere was warm before. And so the impact of these very high levels is they're going to lead to an unprecedented warming in a very short period of time.
So it's kind of the rate and the short time period over which the warming is occurring. Is that the problem?
That's the problem, yes. I mean, methane levels have doubled since the Industrial Revolution. Carbon dioxide levels were about 270 parts per million before the Industrial Revolution. Now it's over 400.
So what does parts per million mean?
Okay, so 1 part per million means 1 molecule of CO2 for every 1 million molecules of air. So it's like the fraction of the air molecules that are carbon dioxide. If you look at the 1 million year history, you see CO2 levels changing and so on, but it has been vertical in the last couple hundred years. Levels are now higher of CO2 than they have been in the last 1 million years.
Okay, so I've got a number. This number basically tells us how warm the Earth would be without greenhouse gases. And apparently it's minus 18 degrees Celsius. So if greenhouse gases provide us with extra warmth, because it's clearly not minus 18 degrees Celsius, why are they such a problem?
That's a good point. Without greenhouse gases, we'd all be dead. The amount of sunlight reaching the Earth, that some of it gets absorbed, some of it gets reflected. If you do calculations without greenhouse gases, you indeed find the surface temperature will be about minus 18 degrees Celsius. So you do need greenhouse gases like water vapor, like CO2 and so on, in order to have a temperature that can sustain life. The difference, though, is that the concentrations of these gases are much higher than they were, and they're going up very fast. So we're going to an enhanced greenhouse effect, way beyond what's needed to sustain life. And so the impact of this will be rising sea levels, because as you said earlier, most of the extra heat goes into the oceans. That expands as it gets warmer. Ice sheets are melting. So it's the rate really that's important. But it's a good point. Greenhouse warming was necessary for life to exist. But you can't have too much of a good thing. If it goes too high, then it's going to be a problem. The extreme is Venus, which has in its atmosphere about 95% CO2, and it's at several atmospheres. And the greenhouse effect there is over 500 degrees Celsius. So that's what can happen if you go to the extreme.
Okay. Is it not possible that climate change could be explained by the natural heating of the sun? Because the sun does go through solar cycles where it heats up and cools down again. Could it not be explained by the heating of the sun?
You're right that the sun does have a solar cycle. It's about 11 years. But actually the percentage change of solar energy during that solar cycle is very small. Far too small to explain the changes in temperature that we've seen over the last century or so. And another natural phenomena are volcanic eruptions, which can release into the atmosphere molecules like carbon dioxide, for example. But again, there have been records of volcanic eruptions in the last 100 years, and if you combine volcanic eruptions with changes in solar output, in fact, it should be slightly cooler now than it was 100 years ago. So those natural variations of things that could impact temperature don't correlate at all with the observed temperature change.
So what was the effect of, for instance, the eruption of Mount Pinatubo on the climate as a whole? Did it really make much of a difference?
Not a big difference, but it put a huge amount of aerosols, so that's very small particles, into the stratosphere, and it enveloped the whole planet. And for a couple of years, the amount of ozone in the stratosphere was quite a bit less. And of course these aerosols also blocked out the sun a little bit, so it did lead to a cooling, but it's just a temporary thing that will then recover again as those aerosols that came from that very large eruption will gradually make their way back down to Earth.
So aerosols kind of disappear while carbon dioxide doesn't?
Well, no. I mean, there is a background level of aerosols in the stratosphere, okay, which is there all the time, but after a major eruption you get enhanced amounts of aerosols in the stratosphere, and so you can get ozone destruction on these aerosols, and so the amount of ozone will suddenly dip, perhaps for a year or two, but then recover again as the effect of the big eruption decreases. But it's not true to say that aerosols are disappearing. It's a steady state concentration. Likewise, down in the troposphere where we live, aerosols are very important as well, because they can scatter radiation, can send them back to space. Aerosols impact how clouds form, and of course clouds reflect a lot of energy back to space, and also trap heat that would otherwise escape from the surface back to space. So aerosols are very important, so that's a topic that you just mentioned that's very important for climate change.
So if we look at the grand scale of things, the global climate is increasing, but what are the local climate implications of the global scale climate change?
Okay, well, if we look at what's happened in the last 100 years, there has been a general warming by about 1 degree if you average everywhere, but it has been different in different places. It's gone up, as I mentioned, 2 or 3 degrees in Siberia, for example. There have been some parts of the world where it's changed much less. So locally it will be very different. And of course, from year to year, as you mentioned, the local temperature is very much driven by our weather, where the winds have come from. It only takes a change of wind direction for the temperature to change quite rapidly. But there are parts of the world where there have been worse droughts over the last couple of decades compared to 100 years ago. There are parts of the world where there's more extreme weather events like monsoons and very heavy rainfall and so on. But of course you've got to make the average over the whole planet in order to come up with a a trend, if you like, with time.
So, in the UK, we constantly complain about the weather. So what would be the harm of having slightly warmer summers?
Well, as you say, some people might say that's a good thing. And some people have also said that if you've got a little bit more CO2, plants will actually grow better. So you're going to get better crop yields. But you've got to balance that against the increased burden of CO2 in the atmosphere, and it's known what the warming will be globally. It's known what the rise in sea level will be. So although parts of the world might enjoy a nicer climate, a bit warmer here for example, there are other parts of the world where a small change of climate, small rise in sea level will have a devastating impact. For example, Tuvalu in the Pacific, and I think on the news yesterday the BBC was live, was it from Vanuatu, which is in the Pacific. Small rises in sea level in some of these South Sea islands will have a dramatic impact. So it's easy for us to think it might not affect us very much, but there are other places where it will have a much bigger impact and more quickly.
So the media portrays carbon dioxide as this evil villain of climate change. Is that the main culprit, or are there other major sources towards the climate change we're currently experiencing?
In terms of the change in climate that's due to human activities, carbon dioxide is the largest part of the pie, if you like. But there are other greenhouse gases which have been increasing, which are also linked to man's activities. For example, methane, nitrous oxide. So nitrous oxide is a gas which is released from soils, but if you apply fertilizers to soils to increase crop yields and so on, you get larger emissions of nitrous oxide. Ozone, which is O3, that's another greenhouse gas, and that's a molecule that's generated as a component of photochemical smog. So down where we live, that's a harmful gas that we breathe in, but it's also a greenhouse gas. And then finally, halocarbons, the replacements for CFCs, for example. These are all very powerful greenhouse gases, and these emissions have been increasing due to our activity. So it's not just carbon dioxide, but that is the largest part of the pie, if you like, for the warming that's been caused by human activities.
You mentioned ozone, and it's quite confusing as to whether ozone is a good thing or a bad thing, because you've just said it contributes to climate change. However, we're told that we should be having more ozone in the ozone hole. So what is the situation with ozone? Is it good or bad?
Yes, location is important for ozone. So in the stratosphere, it's essential because it's blocking out those harmful ultraviolet rays that will cause skin cancers and other problems. So we need the ozone in the stratosphere. So it's a good guy up there. But down near the surface, too much ozone is bad. It's harmful to our lungs, it causes inflammation, it causes damage to plants. In fact, ozone causes more damage to crops than all other air pollution put together. And so it's a bad thing down here because it's harmful both to humans and plant life. So it's bad down here where we live, it's good in the stratosphere where we don't breathe the air in, but it's necessary to protect us from harmful UV light.
So I wanted to actually ask you a bit about your research. I mean, what does it involve, and how does it relate to climate change?
So we've been talking so far about fairly long-lived gases like carbon dioxide, methane, for example, has a lifetime of 10 years. And many of these greenhouse gases are controlled by chemistry. Methane, for example, is almost all removed by one chemical reaction. That's the reaction with something called the hydroxyl radical. So a radical is a molecule that has an unpaired electron. It makes it very reactive. So my research group have developed instruments that we've taken out into the atmosphere to make measurements, that's from the ground or from aircraft, of these short-lived molecules like the hydroxyl radical that do all the chemical processing in the atmosphere. The hydroxyl radical is sometimes referred to as a detergent of the atmosphere. It cleans up our emissions. And so we're interested in these short-lived molecules that do all the chemical processing, and these relate to climate change because in many cases they're controlling the concentrations of these gases.
So would that be, for instance, methane or carbon dioxide?
Carbon dioxide is chemically very unreactive. So the amount of CO2 in the atmosphere is largely related to physical processes like photosynthesis. It's taken up on plants, it's absorbed by the ocean, and so there's not so much chemistry involved in carbon dioxide. But many of the other greenhouse gases, like ozone, like methane, like halocarbons, are removed by chemical reactions. So yes, they are important for controlling greenhouse gases.
So I wanted to ask, you say you take measurements around the world. Well, what's the point of going on a plane, which releases greenhouse gases, carbon dioxide, going across the world and taking measurements? I mean, could you not do that here in the UK? Why do you really need to go across the world to get these measurements?
So a climate model, of course, has got to consider changes in temperature, changes in other parameters globally. And the chemistry in different parts of the world is different. If you go to a tropical rainforest, there'll be very high levels of emissions that have come from plants. If you go over the oceans, there will be emissions of bromine or iodine species from the oceans. Of course, if you go to more polluted regions over Western Europe or North America, you've got much higher levels of nitrogen oxides and other emissions, hydrocarbons, for example. So you need to understand the chemistry in each of these locations in order to put together a climate model that's going to describe the whole of the planet. So
it really is justifiable going across the world.
That's right, yeah.
Measurements.
In fact, some of our first measurements, we deliberately went to the north tip of Tasmania, to a place called Cape Grim, where we wanted to understand the chemistry of the atmosphere that had not been perturbed by man's activities at all. And so the air that came into us in Tasmania had spent the last 2 weeks or more in the Southern Ocean. There had been no fresh emissions at all from our activities. So we were able to measure the concentration of hydroxyl radical and understand the chemistry in the background atmosphere. Then we went to other locations, as I mentioned, forested regions, more polluted regions over land and so on, where the chemistry is different. So we've been focusing, I think, mainly on greenhouse gases, but of course air quality is another thing that's very important in society at the moment. Our air quality is deteriorating, the levels of harmful substances like ozone and nitrogen dioxide is increasing, and so it's chemistry that's controlling many of these things. So it's also important to measure in areas where air quality is poor, as well as just focusing on greenhouse gases.
Well, the ozone hole was pretty much, the problem of the ozone hole was resolved in Montreal in 1989. Do you think that climate change can ever be fixed?
Well, even if we stopped emitting CO2 tomorrow, it's still going to take millennia before the sort of follow-on impacts will have finished. For example, the warming of the oceans and so on. There's a very, very long lag. So I think what we've got to try to do is to limit the warming that will take place in the coming centuries. This very large climate summit that's taking place in Paris at the moment, the aim is to try and limit the increase in temperature to 2 degrees above what it was in the pre-industrial region. So we want to control the amount of CO2 and other emissions so that the warming due to those will lead to a further 1 degree increase approximately by the end of this century, which will be 2 degrees above what it was pre-industrial. So the aim is to limit it at some value that we think will not lead to problems that are not insurmountable. The problem is that the amount that we're emitting at the moment, it's felt unrealistic that we'll be able to achieve this 2 degrees. And there's been many climate models that have been run to say what's going to happen at the end of the century. And I think the average of those is showing it's going to be higher than 2 degrees. So I think we're probably not going to meet that. So we are trying to limit it, but we're not going to be able to stop it happening, because it's too late for that. We've already put too much CO2 into the atmosphere. It's about damage limitation now and keeping it at a reasonable level in the future.